Let's look at problem number 1 from an old exam number 2 from ECE 207. This particular problem wants us to derive the governing differential equation for the capacitor voltage V sub c of t, and we're not going to worry about the initial conditions. We really just want to derive the equations of motion, or the first order differential equation. It's first order because we have one energy storage device in this particular circuit, and because of our mnemonic that we have been doing before, that's not it, is it? We actually want to use ICE in this case, which says that I sub c of t is now c dv sub c dt. Based on that relationship, we now know that the variable of interest is the one that's being differentiated in this expression, I is equal to c dv dt. We want to concentrate or focus our attention on writing our equations in terms of that capacitor voltage. Hopefully it's somewhat clear to you that this looks like a node, or that we need to write KCL equations or nodal equations for this particular problem. If not, we can actually write mesh equations, but let's do it first by realizing that we really only have that one node other than this reference node with which to write equations. We have this current coming in, I sub s, we have this current going out, which is our resistive current, and we have this current down through the capacitor using the passive sign convention. And consequently, then if we apply KCL at node 1, we'll be able to see that we have I sub s, and that's equal to I sub r, here's I sub r, and here is I sub c plus I sub c. And what we really need to do then is to rewrite these variables in terms of this capacitor voltage V sub c. I sub s is given to us. We'll just keep that as it is. There's I sub s. That's equal to I sub r. Another observation that we need to be able to make is that this voltage V sub c is not only the voltage across the capacitor, but it's also the same voltage dropped across the resistor. That allows us then to write I sub r as simply V sub c of t over r, and in this case it's r sub 1. And finally then I sub c is just going to rely on our current voltage relationship associated with the capacitor, and that's then c dv sub c of t dt. And that is our governing differential equation for part A. We could rewrite it if we wanted to and divide both sides through by c and isolate the first order derivative so that we have dv sub c dt is equal to, and now if we divide both sides by c and push everything over to the other side, we now have minus 1 over r sub 1c V sub c of t plus 1 over c I sub s. And that could be a constant, it could be a function of time. Suppose that you didn't see that you wanted to write KCL or node voltage equations for that particular circuit, and you're thinking, oh well, this looks like there's a couple of meshes here, why don't I just write mesh equations for this particular system. We have this voltage V sub c, and we have this resistor R1, and here's I sub s. If we did that, we would have, here's one mesh current, and here's another mesh current. Let's call this particular mesh I sub 2, and we can call that one I sub 1. If we were trying to write a KVL equation around mesh 1, we would have a problem trying to determine the voltage dropped across that source, but we should be able to see fairly easily that I sub s is given to us as the same as I sub 1, or the first mesh current that we need to find is actually just the source current I sub s. Then if we write KVL at the second loop, we have R going from this lower node clockwise. We have R sub 1 times I sub 2 minus I sub 1. That's the net current going up through that R sub 1, and we want to have the passive sign convention. That gives us a positive voltage drop from bottom to top across R sub 1. And now we want to write the equations in terms of the capacitor voltage, and instead of trying to say, oh, well, that must be some integral, let's just say that that's plus V sub c of t, and that's equal to 0. That's KVL at the second node. What we can do now is simply realize that this is I sub s, and I sub 2, if you go back and look at how we defined it, that was actually with the passive sign convention just equal to c dv sub c dt. If we now use this in place of I sub 2, we should end up with the same relationship that we had before, the same governing differential equation. We have R1 c dv sub c dt minus R1 I sub s plus V sub c of t equals 0. If we now divide through by this coefficient that multiplies dv sub c dt, push everything over to the right, we end up with dv sub c of t dt equaling minus 1 over r sub 1 c v sub c of t plus 1 over c I of s, and that should be the same first order differential equation that we derived before for this particular problem.